Hello everyone, my name is Gede Pringgana. On behalf of my colleagues from the University of Manchester in UK and Udayana University in Indonesia, I would like to deliver my presentation entitled SPH Modeling of Tsunami Wave Impact on Low-Rise Structures for the Virtual International Conference on Coastal Engineering. This presentation consists of 5 parts. The first one is the introduction to low-rise building in tsunami, and then followed by research objective, methodology, result, and end up with conclusion and future work. As we know that the 2004 Indian Ocean and the 2011 Japan tsunami caused severe damage to building in the affected coastal region, as can be seen from Figure 1 and Figure 2. Based on literature, the damage was due to excessive force acting on the vertical surface of the low-rise building. A building categorized as low-rise if it has less than 7 stories. To improve the resilience of low-rise building subject to tsunami, the strategy that can be implemented is the use of either the breakaway wall or opening, as shown by Figure 3, to allow tsunami flow through the building. Alternatively, the position and orientation of building relative to the direction of oncoming tsunami waves can be modified as illustrated by Figure 4. However, the effect of building's orientation on the force applied at the building's vertical surfaces is not fully understood. This study has 2 objectives. The first one is to examine the influence of building orientation on the tsunami-induced hydrodynamic force, and the second one is to observe the effect of the group of buildings layout on the inundation flow. This study employed numerical modeling using smoothed particle hydrodynamics to simulate the interaction of tsunami wave and building structures. SPH is a method that's capable of simulating violent wave impact, include tsunami. For all models in this study, we utilize the SPH-based software Jewels Physics version 5.0 that has just been released last month. Prior to this study, we have been conducted convergent study related with the SPH particle size by simulating the Cliffsman-Dambrick case, where the numerical result in good agreement with the experimental data. Moreover, we have simulated an experimental case of tsunami-like wave impact on vertical wall that was conducted in the tsunami wave basin at Oregon State University, and the result has been published. We have also published a technical paper about the 3D simulation of tsunami bore impact on discrete structure and combined with finite element modeling. Figure 5 shows the side view of boundary model in the form of water tank that is used in this present study. It consists of offshore part with water particle and onshore part where the structure is located. The multiple solitary waves were generated by the motion of pedal located at the left-hand side. In all simulation, 2 solitary waves were generated, and the reason for implementing multiple solitary waves was due to the fact that tsunami consists of several waves, and the second tsunami could bring greater energy, so it was to be considered. The cube represents the low-rise structure where it is considered as low-rise since the ratio of its height to the wave height is equal to 1. The I symbol in the tank means that the pressure distribution on the vertical front surface of the cubes can be seen from the back of the cube by setting the cube as a transparent structure. Based on the previous convergence study and related works that have been done, as a rule of thumb, the diameter of particles should not be greater than 1/10 of the smallest length of the structure. And this present study adopts a particle size of 0.04 meter, where the number of particles involved in the simulation are about 2 million. The total time of simulation is 12.5 seconds. These are 4 simulation cases in this study that include 1 case with single structure and 3 other cases with multiple structures to observe the effect of structure's orientation on the inundation flow and the impact force. The multiple structures were rotated 30 degree and 45 degree clockwise in case 3 and case 4 respectively. The calculation of force is based on illustration in figure 6, where the force is the product of pressure times area, where the pressure measuring probes lies within. The measuring probes were mounted on the vertical surface of structure and equally spaced with spacing equals to the particle size. The total force is the summation of all force on the surface of structure. In this study, the force that is considered is the force in x direction. For unrotated structure, the force is in the same direction with x-axis. However, for rotated structure, the force should be resolved in x and y direction. Based on this diagram, the total force in x direction are given by the summation of F1x and F2x. The solitary wave propagation and the following impact on onshore structures can be seen through this animation. So here we can see the first wave and then followed by the second solitary wave. The effect of structures layout and orientation on inundation flow can be seen from this 2D simulation. Figure 7 and Figure 8 show the detailed pressure distribution on the vertical surface of the rear structure C. The pressure distribution can help the structural engineer to predict the most vulnerable part of the structure during the impact. Figure 9 is an example of the detail of loaded areas at the vertical surface of rear structure C in case 1. The second wave impacted larger areas at the time where the force is maximum. The inundation flow, maximum velocity, and total force impact will be shown in this slide. These are the maximum velocity and impact force for case 1, case 2, case 3, and case 4. The onshore maximum velocity were measured at the center line of the water tank. Figure 10 tells us that at onshore area, the rotated front structures amplify the velocity of inundation flow as it passes the gap between front structures. Figure 11 shows that the second wave impact occurred at longer period of time, and we can clearly see that the 45-degree orientation in case 4 significantly reduced the total force as compared to other degree of orientation. To conclude, the result given here underline the potential for improving tsunami resilience through appropriate positioning of structures. The magnitude of reduction in total force observed for case 4 could in reality mean the difference between survival and collapse. Importantly, such large reduction in force may provide an economic solution to building resilience in developing countries prone to tsunami. For the future work, the numerical modeling technique in this research can be used to investigate the effect of innovative coastal protection that can be developed to protect the coastal communities in tsunami-prone regions of the world. This is the end of my presentation. Thank you very much for your attention.